In this lesson, we are looking into scenario number 2 of chapter 7.4, which we are looking at ladder on a wall. Now, ladder is a very common type of question in this particular topic. So as I've mentioned before, there are 3 scenarios that the question like. This one, the ladder, comes up the most frequent. The difference between this lesson and the previous one about the rod on a peg is that just the forces on it will be different. So you have to understand where the forces come from. Just a quick reminder on the previous one, when you have a rod on a peg, you have the weight, and then on the ground, you've got the reaction supported from the ground and also friction against it. Now, why is it to the right? Because without the friction, the rod will slide to the left, and therefore the friction has to be against it. And then you've got reaction on C from the peg, which will be perpendicular to the rod. All right. So, quick reminder again, what have we done? Upward force equals downward force, left equals right, because resultant force is 0. The whole thing is equilibrium. When the force is not up, down, left, right, then you have to resolve it. For example, RC has to be resolved into X and Y, then you can use up equals down, left equals right, and then once you finish that, you should have 2 equations. Sometimes you can simplify them, but sometimes you can't. Like the previous example, we can't simplify it until the end, but that's fine, leave it there because you know you'll need it later. Remember, in the mechanics, you don't have to do question by question. You can just follow the same step and they will just tick off whatever you've done. So you don't have to follow the order of the question. That's what I'm trying to say. Step 2, take moments at a point, and then take moments at a point, and then do all the moments. Clockwise moments equals anti-clockwise moments, and then it's time to use the previous 2 equations you've set up, and then you can find out the rest of the variables. So to the lesson, what's different is that the dynamics is sort of different. You have to understand what the forces are on there. So let's go. Right, so remember this famous diagram, okay? So if that's a wall, that's a ground, okay? Right, so one day you hang out with friends, okay? You said, okay, let's wait in one of the tube station, one of the train station, but your friend is late. Then what do? You go to a wall and lean on it and wait for, and while you moan and text your friend why you're so late, just do all the funny emojis. Okay, funny means passive aggressive, like a smiley face. And why are you late? And then smiley face. Why are you late? And then and that's make them feel the rage, but politely. Anyway, so you're leaning on the wall. Okay, so leaning on a wall. Now I want you to think about when you lean on the wall. How do you feel the support from the wall given to you? Okay, so on your body, I don't like full screen, So on your body, this part we'll talk about, this part of the body, okay? How do you feel the support from the wall, on this part of the body in particular? You will feel, it's this part, you will feel the support from the wall is perpendicular to your body. So there will be a support like this way, wouldn't it? Okay, that's why you want to lean on the wall, because it takes the weight off your body a little bit. What else? Now, you're not on a playground, you're not on a slide, so you're not going to slide on the wall like a slug. So there will be support from the floor, okay, friction. Now, because you're not sliding down, therefore the friction must be against it, there's friction. And the ground is providing firm support, there'll be reaction. And what's this support from the wall as well? It's also called reaction. Because there are 2 R, we can't use the same letter, so we're going to use RA, RB, etc. You can see that the force on the floor is quite similar to the previous one, to the previous example. So what I'm trying to say is this part is quite similar to this part. All right? So let's draw a diagram on there. Let's do the actual one about ladder. So let's read the question. A ladder AB of mass M and length 3A has one end A resting on a rough horizontal ground. Rough means there's friction. And the other end B rests against a smooth vertical wall. So there's no friction on the wall. A load of mass 2M is fixed on the ladder at point C. So that's 2M. So let's draw a better diagram, better than the one on the right-hand side, waiting about a friend. Well, this guy probably would have no chance waiting for a friend. The friend is always late. So don't be the friend that's always late. I'm always there, you know, as a person, I'm always there, usually 10 minutes earlier before my friend. And then what happened is, end up waiting 45 minutes. But it's a lesson for me to learn. Right, so anyway, okay. So here's a wall, so that's point B. Okay, so point B, there'll be a reaction coming there. Let me use different color for the forces. Oops. So force. This force is called RB. Okay. And then what else have we got? A load, so a mass M, 3A. So the whole distance is 3A. Now you see I use different color for distance, so I don't get confused with the force and the distance. A load of mass 2M is fixed on a point C. So the point C is here. 2M, therefore there'll be a 2mg shooting downwards because it's a weight. So I'm good. It's fixed on a point where AC is A, so that's A. And therefore this will be 2A. Okay, I don't know if that's going to be helpful, but you know, I'm going to write down. The letter is modeled as a uniform rod. So uniform rod means the mass of AB is down the middle, so that'll be right down here. Mg, the mass of the letter is M, down the middle. So that this will be 0.5A because the whole length is 3A. Therefore, this length will be 1.5A because that's A, so that has to be 0.5A. Next, what else? Molecular wall. The leather rests in limited equilibrium at 60 degrees on the ground. Find the coefficient of friction. Okay, so I want to find friction. Find the coefficient of friction. That's 60 degrees. So that's 60 degrees. Right. So first question. On the ground, what forces are on there? There's a reaction of A. We talk about that. And then also friction in here, F of A. So these 6 forces, well, no, hang on. 2mg is a special for this question, but if we ignore 2mg because that's only happening in this question, normally if reaction on A and friction on A, so that's standard. Leather leaning on a wall, you've got a friction, you've got a reaction shooting out from the wall, and that's a support from the wall. Again, that's a given. And then the mass of the leather. Okay, so that's 1, 2, 3, 4. You have something you have to remember. I want to say remember, but as in you understand it, then next time you can just perform it. Right, so once you finish, remember the first step, upward force equal downward force. So upward force equal downward force. Let me bring this diagram next to me. It's the best diagram ever. So first step, up equals down, left equals right. So 2 equations, we accept 2 equations. There are no forces that are diagonal, so perfect. So no diagonal force, so no resolve. So I'm going to put it there. You don't have to write it, just for a reference. So no diagonal force, no resolve, no resolving, whatever. You know, English, not a problem. So up equals down. So what forces are up, pointing upwards? RA. So RA equals downwards to mg plus mg. So RA equals 3mg. You know I am always against g. So g is 9.8. 3 times 9.8 is 29.4. So RA equals 29.4 m. Don't forget the m. So that's the first equation. To set the second equation, left equals right. So what forces point to left? We've got RB point to left. So RB equals the right force, F of A. Friction equals mu R. So RB equals mu R. But because this friction comes from A, therefore the reaction is also A. So again, F equals mu R. Okay. Right. Can we substitute anything in? Yes, we can, because RA from the previous one, we've got RA equals 29.4. So I'm going to sub it into here. So RB equals mu times 29.4 m. Nothing we can do in here. RB equals 29.4 mu m. So in here you can see there's so many variables, we can't really solve anything. So we're going to leave it like this. But one thing we've done in here is we have sort of simplified two equations into one. So this equation RB equals mu RA and RA equals 29.4 M, we sub into one. So now we've got one to work with. Okay, so instead of two, now we have one combined. Second step, take moments at a point. Second step, take moments. I'm going to use black for, so step 2 for green, but what you have to write is in black is what you have to write in exam. Take moments at, in this case, I'll probably take moments at A again, because at A there are two forces on there. The question is, how many forces do you have to calculate moments with? How many forces do you have to calculate moments? The answer will be 3. 2 mg, mg, and RB, right? So one by one. So 2 mg. Now, when you think about A is the pivot, where is the perpendicular distance from A to the 2 mg? How can you draw a perpendicular line from A to 2 mg? It will be right here, wouldn't it? Hang on, I can't use. It will be right here. That's your perpendicular distance. Right, that's your perpendicular distance for 2 mg. And what about mg? It will be that one here. Right, so 2 mg, let's do one by one, 2 mg. Now, if you are good with moments, if you're familiar with it, what you can do is you can also do the direction first, and you can write in one line. I'll show you how. So first of all, 2 mg, if A is the pivot, 2 mg will be clockwise. Mg will also be clockwise, but the RB will be anti-clockwise, right? So for 2 mg, so I'm going to do clockwise moments equals anti-clockwise moments. So what is a clockwise moment? 2 mg. So 2 mg, the force, times the distance. So what's the distance? Again, the distance is what I highlighted in blue, this horizontal line. That will be A cos 60. So 2 mg times A cos 60. So that's the 2 mg, the moment for 2 mg. What else? What about the, actually, let me bring this down. I need a bit more space. Right. So what about the mg? So the moment for mg will be force mg times the distance here. The distance here will be 1.5a cos 60. So plus mg times 1.5a cos 60 equals anti-clockwise moments. So the anti-clockwise moment is from RB. Question is, where is the perpendicular distance from A to RB? So how can you draw a perpendicular line from A to RB? You can't draw in here, because if you try to make a straight line, here's a ruler, I try to draw from A to RB, that's not perpendicular. So where's the perpendicular line? If you remember the trick you've learned in chapter 4, you can extend the line. You extend the force like this, so that's your RB. And then that's where your perpendicular distance is, from here to here. So that's your perpendicular distance. So that's your perpendicular distance. So this perpendicular distance will be, now if there are two ways you can do it. You can either do, I prefer to use 60 degrees, so you can remember 60 degrees, so 60 degrees here, because of a set shape. So that will be 3a, it's a bit messy. That will be, so that will be 3a in here, 3a cos 60. So 3a cos 60 will become the distance, the vertical distance, right? So plus, so force is RB times 3a cos 60. Right, so if you need help, if you don't understand what's going on in here, you can draw little triangles just to help you. So in here, you can see that's the A, that's 60, that's distance for this 2 mg. For the 1.5a cos 60, you've got the 1.5a, the 60, that's your distance. And for RB, you can do this. That's your 60 degree. That's your 3a, and that's your distance. Okay, so not 3 cos 60, sorry, 3 sine 60, my bad, 3 sine 60, sine 60, 3 sine 60. Right, so once you've done that, then it's time to simplify things. So what I'll do is, in a calculator, I will put in 2 times g times cos 60. So 2 times 9.8 times cos 60 is 9.8. Lovely. 9.8 MA. Plus, for the second one, I'll do g times 1.5 times cos 60. So 9.8 times 1.5 times cos 60 is 7.35. So plus 7.35 MA equals, last one, I'll probably do 3 times sine 60. 3 times sine 60 is 3 root 3 over 2 a times RB. Now you see each term as an a, so I'm going to divide all the a's. We write once, left hand side, these two are like terms, so add them up. 9.8 plus 7.35 is 17.15 m, which equals 3 root 3 over 2 RB. Now, see, our setup before help us to work out RBs because we've got RB in here. So RB equals 29.4 mu m. What you can do is you can use a pencil to bring it down. Bring this down. I'm good, right? 17.15 m equal 3 root 3 over 2 times 29.4 mu m. So that RB becomes 29.4 mu m. So you will see a pattern of how we use the previous equations. Once you've done all the 3 steps, it's time to use all the 3 equations that you've used before. You've created. Both sides have an m, so I'm going to divide both sides by an m. So you can see, to find mu, I can do 17.15 equals, on the right hand side, I'm going to do 3 root 3 over 2 times 29.4. That will give me a really messy decimal, 76.38 mu. So 17.15 or mu equals 17.15 divided by 76.38. Now I'm not storing this value because it's only your last step. And the question in part B do not need us to do further calculation. So mu I got 17.15 divided by hang on, sorry. So 3 root 3 over 2 times 29.4, 17.15 divided by answer, but 0.225 in 3SF. There's no unit for mu. All right, so that's the answer. Again, this question will probably worth 8 marks, 7 marks, 8 marks quite easily. You can see why. Lots of steps. Part B, state how you have used the assumption that the letter is uniform in the calculation. So maybe you can tell me what's about uniform. Uniform is that the weight of the letter is right in the middle. So part B, you can say part B, the letter is uniform. So the weight of letter is in the middle. Okay, and that will be the end of the letter question. So again, quick one. What are the forces on the ladder? First of all, on the ground, you've got reaction from the ground upwards and then friction against it. You've got the weight of the leather right in the middle. Sometimes it's non-uniform, be careful, but there's a weight of a leather. And then also there's a perpendicular distance shooting up, perpendicular support force shooting up, reaction force shooting out from the wall. And that's the end. Upwards equal downwards, take moments, clockwise moments equal anti-clockwise moments, and then use all the equations you have set up before and do some algebra and solve the answer. Okay, and that's the end of scenario number 2. Next time, we'll be looking into scenario number 3.